Well, I want to welcome you here to the top of the Southern California batholith here in Southern California and most of San Diego County, of which this particular geologic feature makes up. What is a batholith? Basically, it is a large granitic body, larger than 52 square miles in size. Now, this particular batholith, the Southern California batholith, is measured from Riverside County all the way down to Cabo San Lucas in Baja California. So as a granitic body made up of many pieces, but all in one feature, it runs about 1,000 miles long and about 100 miles wide. Now, we are on the eastern edge of that batholithic structure here in San Diego County. That is the Southern California batholith that has lost its top. It is now, through erosion, more of the granitic bodies starting to appear. Well, here we are, here in Ranchita, which is a small settlement at the top of the batholith here before you enter the downward grade of Montezuma Grade going into Anza Borrego State Park. Now, you can see over my left shoulder here some rounded boulders there. Now, those are typically what you would find as the erosional pattern for granitic rocks of the Southern California batholith. In higher mountains around us, that's all part of the San Ysidro Range, which are one of the mountain ranges that make up the high elevations of the Southern California batholith as it has been eroded since the last 2 million years. 2 million years ago, much of this was relatively low-lying foothills. And over the time, as the batholith continues to push upward, it pushed up much of the territory we have here. Where we're standing here in Ranchita, we're at 4,000 feet. Much of the elevation change that's going down is allowing for materials to literally fall towards the trough. It's falling towards the Salton Sea, east, where the San Andreas marks the former boundary of the Farallon Plate, which subducted 20 million years ago. Much of the typical shaping that you see for erosion for granitic rocks, you'll see here. It tends to be rounded, fairly smoothed out, not a whole lot of jagged pieces. Physical erosion from wind throwing grit against the rocks will tend to round out granitic rocks. Stacked boulders that have the rounded appearance, almost spheroidal in some cases, and very typical of the kind of erosional style and pattern of now newly exposed granitic rocks. Now, these rocks here have been exposed for at least the last couple million years as erosion has stripped away the former seabed, and we're looking at high points here that have been pushed up by continual material underneath the batholith, molten material, pushing up against the body, and as it does that, the material on top starts to push upward. In effect, we are pushing out of the sea and onto becoming dry land, and then becoming an exposed land subject to all the agents of erosion. Typical landscape is what we see here in the Culp Valley area of Anza Borrego Desert State Park. Crawford Overlook. We're looking at a boundary area for the cataclastic zone or the shear zone that's marked on the maps against the rocks that at one time used to be part of the upper portion of it and now slid down through partly through erosion, partly through fault action. Now, if we're looking down and we're coming down from the skyline, we'll pan down slowly and you'll see that the rocks here on this steep slope tend not to be very rounded. They don't tend to be very tall, but they do tend to be rather flattish, almost as if they've been squeezed out and laid out to rest onto the surface of this slope. That's a good indication of the internal structure of the minerals that have been pressed and moved to realign themselves due to the pressure of this shear zone or cataclastic zone. So when the erosion occurs, the minerals, as they are break down based off of the orientation of those minerals. And in this case, because they're laid out nearly horizontally in a line, much of the roundish effect that you would get in the undeformed rocks that we saw at Cove Valley. We're not seeing the same effect here. As we continue to pan on down, we'll go down to the bottom of this slope to a stream bed that has been created through erosion over the years. And down at the bottom there, we're going to find that that's going to be the exposed boundary between the cataclastic zone, which is going to continue underneath the darker and more rounded rocks above them or to the south. The stream bed here, and pretend now that it's a demarcation between two layers of cake. And the upper layer used to be on top of the what we were defining as the cataclastic zone, and because of gravity, because the area here has been overturning and uplifting, this upper layer of the cake has now slid down, and in this case eastward, away from the cataclastic zone. But if we were to continue to look for the cataclastic zone and kept going into the ground, we would find it would be still underneath this darker, less deformed rock that makes up this upper layer. So gravity is taking effect over time. Faulting is taking effect over time. The layers of the cake are losing its stability to stay one on top of the other. Instead, gravity is starting to make the layers slide, one past the other. And what we're seeing here is one layer that has slid past another. The cataclastic zone on the bottom, the upper layer that used to be on top now away and slid down. And since the whole region is also turning, the cake is turning over, it is also breaking up, and it too is breaking apart in blocks, and those blocks are sliding forward, or in this case downhill and to the east. So more of the cake is breaking apart. Again, as the whole cake itself has been upturned on its side, facing east in this eastern part of the Southern California batholith. Now that we've kind of set the table as to how this cake is oriented, we're now going to go see the icing that used to be on top of it all before the cake ever got turned over. And that will be, ironically enough, at the bottom of Montezuma Grade, from 4,000 feet down to 800 feet in elevation. That's going to be the icing, the leftover, the former seabed, and now the remnants of all of that left over. So that will be our next stop.
And with the change by heat and pressure, we're finding that these sediments are now no longer true sediments. They are what we call meta-sediments. They are starting to metamorphose through heat and pressure into other rock forms, quartzites, possibly some shales, certainly very, very hardened mudstones and siltstones. These sediments would indicate a relatively near-shore environment, and one that after over the long course of time, having been buried and now being pushed over as they were exposed by the erosion over time of the batholithic rocks, these rocks themselves are undergoing a great deal of erosion. They are reducing in their breadth and width and thickness, but still maintaining some resistance to erosion because heat and pressure cause a change in their internal structure so that they're harder and more resistant. This is the top end of our story, even though it's at the bottom end of the grade.